interwebs, welcome to Let's Fix Computers. I've got a MacBook Pro here. This is a 2 Thunderbolt port version. Not sure what year, I think it's a 2017 or maybe a 2016, and it does not turn on. So press the power button and nothing happens. Now, I'm kind of scared of the modern MacBook Pros. I don't know much about them in terms of board repair. However, I think I might have a good starting point here. What I've got, this is my Pine 64 Pine Power desktop, which is the USB power supply that I use. This normally sits on one of my other workbenches with a bunch of USB stuff on charge. Very useful bit of kit. However, it's got PD65 on it, which is power delivery, which is what MacBook Pros use. So I can also use it for charging MacBooks. The interesting thing is that I can immediately have a rough guess as to whether I'm on for a winner or not. If I plug this guy in, it will tell me if it's negotiating power. So it's gone to 5 volts. Now it's gone up to 20 volts. So from here, I can straight away see that the Thunderbolt ports are negotiating power delivery. So that tells me something. I can also see that it's drawing 0 amps. Now, one of the weaknesses of the Pine Power desktop is it's not very good at detecting low currents. So if the current is, say, less than 100 milliamps, it probably won't register on this thing at all. 100 milliamps is a bit hit and miss. Really, this thing's not very good at less than 200 milliamps. However, it's a USB charger. Generally speaking, you're not plugging anything in that would charge any slower than that. Not the point. Anyway, so we've got low or no current draw here, but it is negotiating 20 volts. So from that, we can deduce that it is not charging and it probably just has a flat battery. So let's get the back cover off and let's do a little bit of probing and see what we can find. So these things are a bit of an animal to open up compared to the older MacBooks. We've got the usual pentalobe screws on the bottom. And then what we need to do is we need to pry up the sides. And there is a clip here and here that we need to pop open. So I'll pop those clips open, and then the cover needs to kind of slide that direction to release catches along the back, and then it will come off. So I'll just whiz through that in fast forward. It's a bit of a pain in the ass. Be careful if you're doing one of these for the first time. They are not like the older Macs, which again is why I'm kind of scared of them. Okay. Right, visual inspection. None of the liquid damage sensors have gone off. The first thing I'm going to do is disconnect the battery and reconnect it again. And we'll just see if it comes back to life after that. You never know, I might be that lucky. So the batteries on these are hidden under this cover here. I'm just going to very gently pull this back. And there's two parts of this. There is a data wire going across, and then there's the actual battery strap, as it were. So let's just peel back a little bit of plastic there. Undo the ZIF connector with a flick of the fingernail and disconnect that. And now we've got a T5 to undo that battery connector. Put that to one side, and I'm just going to bend that upwards in one movement. There we go. So that's our battery now disconnected. So I'm just going to leave that for a sec, and then I'm going to come back, connect that all back up, and just see if the laptop comes back to life. Right, that's had a polite couple of minutes. I'm going to load up this, and I'm going to try not to bounce the battery connector here. So I'm just going to shut that, hold it closed, and put the screw on. I don't know how delicate this is to a very, very shoddy connection there. I don't like this one bit. I always get the feel that when you're putting that in, you're getting a really rough connection as you screw it down, which seems like a bad idea. But then on the other hand, with no data connection either, theoretically, the laptop shouldn't attempt to draw current until it can communicate with the battery. We have no current draw. Okay, that didn't do anything. If I just press the power button, does it do anything? No, that didn't do anything either. Very well. I shall close it again, and I will disconnect the battery again. And we're going to go looking for short circuits, I guess. Once again, I'm flying blind here, in short. Not familiar with this logic board at all. So, let's see how we do. At this point, I spent some time trying to figure out the board without opening schematics. This isn't necessary, but I think it's good practice to see if you can understand a board layout before looking up the answers. However, MacBooks, and especially the modern MacBooks, are so densely packed and integrated that they're really not good candidates for this, and I just wasted a lot of time poking at it. So we're going to jump forward to when I get the schematics out and actually start making progress here. If you're interested in the blind fix approach, I've got other videos about that in the board repairs playlist. There we go. That wasn't too bad. I think what I'm going to do, I'm going to see if I have a schematic for this so we can look at the schematic and find out what the hell this is, and we can probably make some predictions as to what we're supposed to be seeing. So, what board is this? This is an 820-00840. Let's see if I've got one of those. Alright, we're in business. So I've opened the board view and schematic with Flex Board View, courtesy of Paul Daniels. Thank you very much. And let's just zoom down here and we can have a look. And as you can see, we can just see the board layout that we were looking at. And we can now start just having a look and seeing what all of this stuff is. So we've got U3100 and U3200. What are these? Those are resistors. So they're possibly current sense resistors. Fair enough. What are these? So Q is going to be MOSFETs. So as predicted, we have MOSFETs here. So really what we need to do is find out what these are doing. So I'm going to start with the guy that had the problem, which was R3360. So if I switch to the schematic and search for R3360. Okay, so these are the lines coming from the USB Type-C connector. They're CC, which is probably constant current or something like that. And these are the power lines. And this appears to be a control switch to turn them on and off. Now, something that's occurred to me is that if we have a look at the actual connector here, we've got the top and bottom row of connectors because it's a reversible port. So what I've just realized is that CC1 is one side and CC2 is the other side, unless I'm mistaken. Right, let's try a different approach here. Instead of going to an area that I don't know, let's go to an area that I am familiar with, and that is PP-Bus G3 Hot. So let's go and find out how PP-Bus G3 Hot is created on this. So I will search for PP-Bus _ G3H. Here we go. Here's a more familiar page. So, well, I say familiar. It's amazing how different this is to what I'm familiar with. But, so we've got from USB source on the left here. And it goes across. It goes through a bunch of current sensing. It goes through what looks like an inrush limiter. And it comes out through a fuse as PP-Bus G3 Hot. So we know that this is probably not here. Firstly, L7030, where is that? So L7030, it is that big boy inductor that I thought it was. So there was no power there. So we know that there is no power going through this area. So have we got power up here? So we could measure this at R7020. So where is R7020? So R7020 is to the left of the big inductor. And we do have 20 volts there. All right, now we're cruising. Right, so the Thunderbolt power supply does work. Right, okay. Right, so we have power at R7020. We have power here, so presumably there is power going into Q7030, which is a dual MOSFET package. And we need power to come out into this inductor, and there is no power coming out of this thing. So that requires these gates to be activated. And those are controlled by U7000. So, is U7000 on? Does it have power? Let's see. Where is the power pin to U7000? That must be this one here, P in, because that has a wire going up to this power rail. So there should be 20 volts coming down to here. So it's almost certain that U7000 has power so long as there's nothing catastrophically wrong with it. Where is U7000 on the board? That's this little guy down here. Where am I? I'm on the back of the board. So U7000 is this guy here, this little shiny boy. So firstly, let's make sure that that is getting 20 volts. We've no reason to believe it isn't, but let's double check. Its power pin is B5. That's it. PP DC in G3 hot charger. All right. And that is row B, pin 5. Now that does line up with what we saw on the schematic. So now we know what the layout of the schematic is in reference to this pin array. If we look at the schematic, this said B5. So that's going to be row A, because there's pin 1. So B, 1, 2, 3, 4, 5. So now we know how the pins line up. So we want to measure that. Does it have a test point we can get to? And it has a test pad just to the top right. Let's get the multimeter on that. It's that guy there. And there is 20 volts. So there is indeed 20 volts going into this chip. All right. I think I'm going to go and get some advice on this one, because I'm not sure why this guy isn't turning on. And I'm going to see if I can look up some resources that might tell me. So I shall get back to you when I've done that. Right, just as I cut the camera there, I just had another sudden thought. This is not behaving like the normal inductor of a secondary power supply would. Let's go back to the schematic. Normally on a secondary power supply, we would find that we have MOSFETs, then an inductor, then the output. But on this one, the inductor is actually between the MOSFETs, which means when I checked the resistance at this inductor, I was not seeing the resistance at PP bus G3 hot. So I haven't actually checked for short circuits there, because the inductor is not at the output, it's in the middle. So what's the resistance at F7000? I'm glad you asked. F7000 is here, and if we switch to the board, we checked this guy here, we didn't check this guy here. And if we check that guy there, we see 2 ohms. So we have a short on PP bus G3 hot. We have our diagnosis. Very good. Right, so 2 ohms, a little bit high. I kind of want, on a recent video, we talked about a short circuit that was a couple of ohms. And you can't necessarily just inject into that because you have to start ramping up the voltage when the ohms are high. What we need is, we want that short circuit to be 1 ohm or less for a sure thing. And we don't have that. So 2 ohms, could that be something else? Well, what else could it be? It could be going through the CPU. However, we have already checked CPU vCore. We did check the CPU inductors, and those were clocking in at like 4 ohms, if my memory serves me. Yep, 4.6 ohms. So we know that that 2 ohms isn't vCore, because vCore is at a different resistance. So that's not it. Have we got anything here that was down at 2 ohms? 8, 12, hundreds, 60, hundreds. So the answer to that is no. So let's have a look around the board to see where else PPBus G3 Hot pops up, and let's see if we can find it at a lower resistance. And what we might find is, if we probe around, we might be able to find better access onto that and see a slightly lower resistance. If I can get that down to like 1.5, that's low enough to inject voltage on. So let's search for PPBus G3H. I'm going to start on the back of the board where there's lots and lots of capacitors. Let's start looking around and see if we can find someone who's at very low resistance. So I checked the power on these, but not the resistance. 2 ohms. Okay, let's go to a completely different place on the board. 2 ohms. That's a really confident 2 ohms. Alright. That might be as good as we're going to get. Let's go all the way to the far side of the board. Ooh, 1 point just shy of 2 ohms. But basically 2 ohms. Okay, we could stick a volt on that and just see if anything warms up. I think I'm going to put a volt onto that and see if I can get lucky. I'm going to see if the magic of the thermal camera can save me here. Because with 2 ohms, we're not going to get a lot of heat at low voltage. But the thermal camera sees stuff that we can't feel. So, thermal camera might save me. And I'm going to jump into the side of that fuse, if it will let me. And I'm going to come in at a crazy angle just to make sure that we don't catch on the side of anything else. That should do. Right, and now I have 2 jumper cables with the short circuit between them. 2 ohms? Ooh, 1.72. There we go. That's low enough. See, the jumper wires are giving me better connection than just the sharp points of my probe onto the board. So that's why that resistance has gone down. So that's good. I think we're on for a winner here. Now watch me take about 10 minutes to get the sodding FLIR to work. People have been asking me what thermal camera I use. This is a FLIR 1. I can't say I recommend it at the moment. It's finicky to make it work, but that's because it hates my phone, which is a Huawei P20. However, also when it does work, I don't know, it doesn't have great calibration. Like you'll notice I've got to keep my hand in shot in order to keep the relative calibration, and it does the job, but I don't want to say it's a great product. However, it's the only one I've tried, so... Right, here we go. So we've got the thermal camera out. Now watch out for shiny bits like the SSD here. That guy has a shiny surface, so as you can see it's reflecting light from my hand. If I take my hand off Oh, it's getting heat from everywhere. Anyway, it's shiny, so it reflects stuff. So that's misleading. So watch out for anything that is shiny. That's not what we care about. So let's come all the way up here, and let's turn on the power supply. So we're at 1 volt and 2 amps. Ooh, who's that? Someone over here on the left immediately has flared up at 2 amps of current. Man, thermal cameras, they're magic. They're pure magic, worth every penny. Can I feel that? I've mentioned before, the calibration on this thing isn't great when we're super up close. I did get a tip from someone that you can get laser focusing lenses that turn these things into mini microscopes. I don't have that yet. Anyway, behold, you see this dark spot there? That dark spot correlates to that screw hole. So you can see where the visible light and the thermal camera are out of alignment on this because the lenses are physically separate on the device. So because they are physically apart, they have 2 different perspectives. So at this range, it's completely unreasonable to believe that they could get close. As we pull out, they fall into alignment. However, if we want to actually get up close and personal and get really detailed, we have to account for that. However, we can deduce from the dark spot and the flare above it, dark spot, device above it, and then ignore the focus, dark spot, item above it. It's probably that capacitor. So what is this guy, just before we rip him off the board? He is in the top right of the board as we were looking at it. I'm just going to turn the board back around to the orientation it was in on the board view. So that is C6445, which is just a basic bitch capacitor on PP Bus G3 Heart. This thing does nothing. It's just a local bypass. Fine. Okay. Very well. So let's remove it from the board. Now, awkwardly, it's really close to these ZIF connectors. So I'm going to grab some Captain tape, and I really don't want to damage those ZIF connectors, so I'm going to see if I can give them some protection. Failing that, I might soldering iron Hero, actually. Let's do something really devious, just for a laugh. Behold, with the power of 2 soldering irons, I can dual wield and remove this capacitor with no hot air. Here we go. Preferably without destroying that really, really small capacitor that's just above it. I'm going to need to touch up the joints. Stand by. Dual wielding will occur. Ugh. I did it. I couldn't say I'd recommend that. Ow, we ripped a pad. Really? Oh, that's unfortunate. That was not my intent. That can't have been my dual wielding technique, surely. Could have been. We were on a very heavy ground plane, apparently. Fine. Okay, what side did we break, and how much of a disaster is this? We killed the ground side, which is not really of any major consequence, because I'm pretty certain we're sitting on a ground plane. Let's take a closer look. Did we break that ground? Or is that just a really heavy ground plane? I don't think we did. I think that's just a really heavy pad. Oh, it's fine. It's just like an anvil. Alright, panic over. So, MacBook logic boards are really heavyweight, and this ground plane is like soldering onto an anvil. It looks like I ripped the pad there, but actually it was fine. If I hit the old boost button on my pine cell here, just to give it the beans, there we go. It's actually fine. Scared myself for a moment there. Right, so here's our stupid capacitor, and we should find that this guy is very shorted. 2.5 ohms, because that's bad probing. Either way, that's a dead cap. And if we go back to the board, and just for posterity, we'll just probe at our injection points. So grounds to power. And our short circuit is gone. Killer ohms. We are WinRAR. Right, so next question, what is that? Through the miracle of the schematic, we can just see what that was. So this was capacitor C6445. C6445. Front right amplifier. Huh, okay. So that is to do with the speaker amplifier, which I'm guessing must be this affair on the back. And it is a 22 microfarad 20 volt capacitor. Time to get out the little baggie of capacitors. And we are looking for code 226. So that's 22 and 6 zeros. Do you reckon that's a 6? Or 225? I think that's 2.2 microfarads. Uh-oh, I don't think I have the right one. That's very annoying. Out of all of these capacitors, I don't think I've got a 220 mic. Right, I'm going to cheat and I'm going to put two capacitors in parallel. I've got two 10 microfarad capacitors here, and in parallel we add the capacitance together. So two of these together on that spot will create 20 microfarads, which is close enough, allowing for tolerances and such. So if you put capacitors in parallel, you add the capacitance. If we put two identical capacitors in series, we get half the capacitance but double the voltage tolerance. So these two 10 microfarads in series, these are 25 volt capacitors. If I put them in series, I'll get a 10 microfarad 50 volt capacitor. So the kind of places where you might do that are for power supply inputs where you need a high voltage tolerance or something like that. However, I can put them in parallel and I'm going to be cheeky and stack them. I think there's space to stack them there. There's a big gap there. Let's try it out and see how that goes. So where I'm struggling on these very heavy pads, I'm using boost mode on my pine sill here. The TS100 can also do this. So what I do is while I'm using the iron, I hold down the plus button and the iron will go into full heat mode. Now, this tip tops out at about 110 degrees, but as you can see, while I hold down boost, it's giving it everything. And while the board is sucking heat out the iron tip, we've basically got the element at full tilt to compensate. And that helps you when you're just struggling to keep the heat there. Of course, a bigger soldering iron wouldn't have this problem. However, it's very rare, I find, where these small electronic irons actually can't do it. But when you are struggling like here, boost mode, don't forget it's there. I'm going to switch to my TS100 that's currently got the knife edge on it. Darn. I really should just move that tiny little capacitor that's in my way. Or I should just actually take some precautions and get the hot air out. I don't want to screw up these hacking connectors though. go. I think we're on. Mad lad. Let's clean up and inspect. There we go. That's not bad. And that will work just fine. Now, if this capacitor was actually in the audio circuit, like it was carrying audio signals, I would not be messing around double stacking and doing stuff like that. We'd need exactly the right capacitor. Otherwise, the audio might be wonky. However, this is a bypass capacitor for the power going into the amplifier. So, arguably, we probably wouldn't need it at all. Arguably, a 10 microfarad might have been just fine. However, the 20 total microfarads double stacks like that, that will definitely be fine. So, let's just check one last time to make sure we haven't randomly spawned a short circuit for no particular reason. So, I think this side is ground. Yep. And bloody hell, the camera is really in the way for the current angle I'm at, so sorry about that. And that side has thousands of ohms. Kilo ohms. Brilliant. Right, I'm going to remove my jumper wires and reassemble this laptop. Roll the montage. That's all of our connections done up and the main logic board screws in. I'm going to hook up the battery now and do a quick test run before I put on all the little covers and the extra little screws, because everything in this laptop has got a little cap over the top of it to stop it popping off, which I've never seen that happen in laptops before. However, I can't imagine they would do it if there wasn't a reason for it, so presumably they feel like it's necessary. Either way, I'm not going to put all of those on until I know that it works and that I don't have to take the logic board out again. I think that's in. Let's do a test. I'll plug in the charger, and if it starts charging, then we win. Here goes nothing. Bang! It's charging! It's turned on! I win! There we go. And it made a noise. It made the I'm on charge noise. It's probably sitting on the charging screen. Yeah, I think so. Alright, I'm going to take that off charge again, put the rest of it on, and then the next screen you see will be a login screen. Right, while I put these last couple of screws in, I'll do a little bit of a waffle on what we learned. So, this was a valid lesson in remembering your basics, or at least remembering what you already know. I came into this video going, I'm a bit scared of these, and you know what we found? It was the same as it always was. Dead capacitor, inject power. The only difference is I spent a lot of time dicking around at the start of this video looking for problems with the Thunderbolt power input, because I was just like, oh, these use power delivery on them, so you know, there's going to be complications there. And what I should have done is put that aside and said, let's start with the bit we know, which is PP bus G3 hot. And if I'd gone straight to that, I would have saved myself a lot of time. And probably a lot of my faffing about will get edited out because it wasn't terribly relevant, but we'll see. Now, there are going to be times where it will be the power delivery system. And at some point, I'm going to plug one of these in and it's going to show 5 volts on my charger. And that means it's not negotiating 20 volts, which is what it should get. And that will mean that I have a Thunderbolt issue or a power delivery issue or something like that. And at that point, I'm going to have to actually sit down and learn how to diagnose that. And I will do that when the time comes. However, there you go, folks. Just because it's new and scary, don't let all your fundamentals go out the window. It might be that easy. And this is the first successful board repair I've done on a Thunderbolt MacBook. There we have it, folks. One fixed MacBook. It's another dead capacitor. I hope you guys don't get bored of dead capacitors because you get a lot of them. However, this is why we do the repetition. Learn this technique and you'll get a lot of wins. Not all of the wins, but a lot of them. Thanks for watching, everyone. As always, my support links are down in the description below, and I'll see you in the next video. Bye.